So we're going to do a few geometrical proofs using vectors. And it says when you're not given specific vectors, you can still use vector addition, subtraction, and scalar multiples to do some geometric results. So suppose the position vectors of 2 points M and N are given right here. So we know the position vector M and we know the position vector N. We can do all sorts of things with only those two vectors. So for example, if you wanted to go from M to N, so this green place is your starting point, this red point is your ending point, but you're only allowed to travel in the directions of M and N, you could get there by first going backwards to O and then going forwards to N. So we could write that. Ooh, it's moved. M to O, O to N, N to O is negative M plus N. You could also take your starting point at the red dot and go to the green dot. And N to M would be first going from N to O and then O to M, new, which is negative N plus M.
Hold on. Wouldn't that be negative? Because you're going from N to M, and the vector is from N to N.
N to M would be negative M.
Oh, N to M.
Yeah.
I see.
Plus M. Or you could have just taken M to N that we found to begin with and done the negative of that, which if you distribute that negative, that would make the M positive and the N negative. So now, this is the next idea. And sort of one of the ways that I envision or help see what's happening with vectors is you've designed a robot that can only travel in direction M and direction N. And you want it to get to point P. Can it do that? How would it do that? How would you tell the robot to go in certain directions? It needs to end up at the point P at the end. That's its charging station. If it never gets there, it's going to die. This could be a sad robot story. So, P is the midpoint from M to N. And we want to write O to P using only M's and N's. Well, if you wanted to go from O to P, you could first go from O to M. So we're starting here, we're ending here, and we're saying I could go and get to this point, and then if I went halfway along M and N, I would get to P. Well, O to M is just vector M. And M to N, we figured out earlier, was just minus M plus N. So if I have vector M here, and minus M plus N there, halfway. If I simplify this, I get M minus half M plus half N, which is half of M plus half of N. Now if I erase this and I go halfway and draw an arrow in green, and I go halfway, I'll draw an arrow in orange. The green arrow is half of M, the orange arrow is half of N. And if I put them together, head to tail, I get right to P. So if we needed our robot to go from O to P, it could go halfway to M, then change direction, go in the N direction halfway, and get to P perfectly. I mean, you could design it so it would go little tiny bits along the way and sort of follow the path from O to P. But with just those two directions, it could get to that point. Later on, we're going, wow, that's the straightest line you've ever seen. We're going to imagine MN as being a line that goes on forever. With this same logic, can you see that you could get the robot anywhere along that line? By just doing some scalar multiple, get to M, and then just do some scalar multiple along that. And with that, we are going to redefine the equation of a line with vectors in 2 dimensions. And that will let us redefine the equation of a line in 3 dimensions, which I guess is not redefined because you have no mathematics right now for what is the equation of a line in 3 dimensions. And it's very messy with our current system. But with the vector system, it's very clean and easy to use. All right, that's where we're going. But today we're just playing around with geometrical proofs. AB and C have position vectors, so we got the vectors A, B, and C, so it's new. Fancier robot that has 3 directions it can move in. It can move in the direction A, it can move in the direction B, and it can move in the direction C. P is the midpoint of AB, and Q is the midpoint of BC. So can we write the green vector and the blue vector in terms of A, B, and C only? Absolutely. So if you wanted to start, again, I'll use this green dot as our starting point and our red dot as the ending point. I could get from the green dot to the red dot by going to A first, and then going halfway along A to B. And A to B, I could easily do that. If I wanted to go from A to B, I could start at A, go back to 0, and then go to B. So O to P would be O to A, and then halfway from A to B. O to A, of course, is already the vector A. And A to B would be going back along A to the origin and then going to B. Simplifying this, and we saw this in the last example with M's and N's, is just going to be half of A plus half of B. OQ, similarly, will be half of B plus half of C. So now our robot is at point P. We want it to get to point Q. Using only the directions of going in A, B, and C. This seems complicated, but we've already got O to P, and we've already got O to Q. So if we wanted to go from P to Q, can you see that you can go P back to O, and then O to Q, and these were already, this one, P to O is just the negative, so we'll have negative A minus negative 1/2 B plus 1/2 B plus 1/2 C. And if we put this together, it says you can get there with a negative 1/2 A plus a 1/2 C. Which is really fascinating because I'm going to draw those on here in purple. That would be a negative 1/2 A. That's a 1/2 C. So if I start this vector on point P, and then I add this vector head to tail, it ends up perfect. Now, initially looking at that diagram, it's not obvious how you would get from P to Q with those directions. I don't know, I find that somewhat satisfying when you put the final vectors in place and it gets you from P to Q just using those directions. And this is the power of vectors, that they're free moving. You can be like, okay, well, I'll just take this vector and move it wherever I want. Oh, this is my starting point. Okay, I'll connect it onto that. Then I'll add the other one, head to tail. O is the center of a regular hexagon, A, B, C, D, E, F. Probably should have named it HEXGON, hexagon. Given that OA is the vector A and AB is the vector B, how could you get from O to B? Using only A's and B's. Well, it's right there. I could go A and then I could go B, so it's just going to be vector A plus vector B. Now I want to start here, and I want to end here. I could do that, right? And there's more than one right answer. But I could do that by going back along this way, and then down again. And it would end perfectly. You could also say, well, I want to go this way and then this way. And you can steal vectors by saying this one here is exactly the same and parallel to that one there. Because it's a hexagon, those all make equilateral triangles, which all have the same lengths. No matter which method you use, you will find out that it's negative B minus 2a's. Starting at C, ending at F. I would take and steal B to A once, twice. So C to F is negative 2 C to O's. And both of those are negative B's.
Would it just be 2CO?
Oh yeah, positive 2CO. Thank you. And C to O is the opposite direction of A to B, and they're parallel, and they're the same length, so they're equal vectors. So just because B is labeled as going from A to B, it's not fixed in that spot. In our other math that we've always done, things are always fixed in their spots. But vectors, we can just say, oh, that's just the idea. We're going to move it wherever we want to. Now we can get to all sorts of complicated ratios. In this one, we've got only two vectors, vector A and vector B. Those are the only directions you're allowed to move in. You've got some ratios that says AB to BP is a ratio of 2 to 1. So that would mean that if this length is 2, this length is 1. If this length were 6, this length would be 3. Because we need that ratio of 2 to 1. In other words, B to P is half of A to B. That's what this ratio means. CQ to QB is 1 to 3. So this is 1, this is 3. As far as fractions go. So going from C to Q would be going 1/4, not 1/3, of the way from C to B. Does that make sense? That going from C to Q is 1/4 C to B. A mistake that I see in this one often is people see the ratio of 1/3 and they want to do 1/3 of the way, but it's not 1/3 of the way. That ratio of CQ to QB means this length is 1 to this length of 3. Okay, so you want to go from A to B. That's easy. You can go from A to O and then from O to B. Again, having the picture, having your starting point here in green, ending point there in red, knowing the directions that you can go, it becomes obvious that I go along there and I go along there. And by doing that, I now have a new defined vector that green vector is now defined as negative A plus B. So now if I want to go from A to P, I can go from A to B, and then this next part is halfway from A to B again, because of the ratio. So putting that in place, we get its 3/2 A to B, which is negative 3/2 A plus 3/2 B. And now we have an orange vector defined. Maybe I should have drawn that in blue since my work is blue. Easy to change that. There we go. It's not blue. We have a blue vector defined. We've got a green vector from A to B. We now have a blue vector from A to P. And since we have that blue vector, you could, if you wanted to, get the position vector for P. Because I could just go back along the blue vector, back along the A vector, or sorry, it could go forward on the A vector, forward on the blue vector, and that would get me from O to P. So what you see that we're doing here is we are slowly adding vectors that we can use for math further on. So now if we want to go from O to P, we can go from O to B and then B to P, or you could have gone from O to A and then A to P. Either one would work for you. And since we already know O to B, that's vector B, and we had figured out B to P to be 1/2 of negative A plus B, we can put this together. And if you go 3/2 along the way of B and subtract 1/2 along the way of A, you're going to get to P. I want to draw it on there, but it's going to actually go, right? This is 1.5 would get me to about here, and then negative A would get me back and end perfectly at P. Vectors are very visual. Draw them out, draw the results out, see if they match. If you want to go from O to Q, how could I do that? Right? I could go from O to C, and then I could go from C to Q. Like, that part is no problem. Now we have to see if we can take those things and relate them to what we already know. O to C, look at that, is the same as A to B over there. So because they're the same length in the same direction, I can just change that O to C to A to B. And because this ratio was 1 to 3, C to Q would be 1/4 of the way from C to B. And C to B is the same as O to A. So now what we started with is saying going from O to Q, pretty obvious to see. I can go from O to C and then go from C to Q. Now it's turned into, I should go, O to Q should be going from A to B and then going from O to A. If we put this into our vectors, this is saying I should go negative A plus B plus 1/4 A put this A to B in brackets. This is this part, negative A plus B. And 1/4 O to A is just 1/4 of A. Putting those together, and we get negative 3/4 of A plus B. Drawing that out. There's 3/4 of A. This is negative 3/4 of A. Drawing this out. This is B. And if I started at O, I just, oh, it's so happy making. Look at it, worked. It ended at Q. It feels like it shouldn't work out that easy. It feels like I should always be like off by at least 4 centimeters, but it's pretty nice. And now we can show that to go from Q to P, here's my starting point. Here's my ending point. Using only the directions of A and B, okay. Q to P, we could go back from Q to O. So getting all of these position vectors is really helpful, because you sort of use the origin as a hub. It's like, oh, if I can get back to the origin and I have every other position vector ready, I can just go back to the origin and then go to my next point. And Q to O, we've already figured out. Well, we figured out O to Q, so Q to O would just be the negative of O to Q. And we already figured out O to P. Combine your like terms and you get 1/4 A plus 1/2 B. And because it's so enjoyable, 1/4 of A would be like this, and 1/2 of B would be like that. So if I started by doing 1/4 of A first, there we go. And then the half would be after that. Oh my goodness. So cool. You have a rectangle, OABC. There is a picture. The length of OA, so you might see if sometimes they'll write it like this, sometimes line segments have a line over top of it. This could have a vector over top of it with bars around it to say it's the magnitude. Different ways you can see a length in different places. Do you ever do this in previous school years where you said line segment with a straight line over the two letters? Right? OA is equal to 8. A to B, that line segment is equal to 6. Vector OA, so there should probably be a vector over this and a vector over that. We've got vector A and vector B. Express two diagonals in terms of A and B. So if you wanted to go from O to B, you could go down here and then over. So that's going to be A plus B. And C to A, well, that would be negative B plus A. So now, how long is O to B? Well, you could just do A squared plus B squared equals C squared. This is your 3, 4, 5 triangle times 2, 6, 8, 10. So O to B is 10. If you took OB and added CA, so O to B, and I add C to A, if we do it with vectors, we find out that it's just two lengths of A its length would be 16. So careful here. Vector OB plus CA does not mean this distance of 10 plus this distance of 10. It means you started at O. If I add those diagonals together, I'm going to go over here 2 to the right. And that length is 16. I'm a distance of 16 away from my original. So I guess what's important to see here is that this does not equal the length of OB plus the length of CA. Does that make sense? You can't figure out each of these. It is just equal to, in this case, yeah. We've done the math already. I like this last one. OA, vectors, what are these? OA plus AC plus CO. If the two letters in the middle are the same, OA and AC will become, I'm not even going to do the bubbles here. That's, oops, that's not, oh, maybe I should do the bubbles. No, here we go. OA and AC is just saying I'm starting at O, I went to A, and then I went from A to C. Do you see that those first two would be going from O to C? And then if you started at O and went to C, and then we're at C and went back to O, we would get, uh-oh, Ooh. Which is the zero vector. Because if you're at one place and you're back to where you started from, that's your zero vector. Your zero vector, these are O's. This says O. This is a zero. Love the English language. Technically, I think an O is rounder and a zero should be higher.
Zero kind of like across.
Oh yeah, you do that just because you can't tell the difference. I don't know. Anyways, that is where we will end for today.